Okay, people are for some reason totally psyched about this, so let's do acid strength sort of things. Okay, when you're doing acid strength, we're really thinking about 3 categories. In my class, your instructor may have explained it differently if you're from a different class. I explained it by the inductive effect. And we're just going to do the quick summary here, so we won't do the major stuff. Inductive effect, polarizability, which is just size, another way to say size, and then resonance. Okay, we'll also talk about the types of problem in just a second. Okay, basically what does this mean? Let's switch here. Okay. So I'm going to give you some quick tidbits, but these are not true in all possible scenarios. Okay, it's best to understand the concept, but we're doing a review session, so we're just reviewing the tidbits here. For resonance, when there is resonance, that makes it a stronger acid. Okay, so when you find resonance, specifically on the quantity weight, it makes a stronger acid. How do you identify resonance? You're looking for double bonds, you're looking for lots of oxygens, you're looking for triple bonds, things like that. Is more likely to have resonance. Best to draw the Lewis structure, but if you want to make a snap judgment, you're looking for those things. Polarizability and size. We're talking about down the periodic table. I'll put PT for periodic table. Going down the periodic table only, not across. Okay, as you go down the periodic table, the acid strength increases. So you're just looking at the periodic table literally. Okay, this here can kind of go in 2 ways. So one is across. I'll put PT again for periodic table. As you go across to the right on the periodic table, because of electronegativity, which is related to induction, you become stronger. So going to the right and down on the periodic table increases acid strength. Across because of electronegativity, and down because of size. Okay, or you can also see this, so that makes it a stronger acid. Also, if you have electron withdrawing groups, and so you want more of these, yes, and you do not want electron donating groups. No, that will make something a stronger acid. How do you recognize these? I'll do a different color. This, you want to see electronegative elements. So if you see electronegative elements on your acid, the closer they are to the acidic proton, the stronger the acid. So for example, you see a fluorine, a chlorine, maybe even an oxygen or nitrogen. The closer that is to the proton that's about to be lost, the stronger the acid. So you see a chlorine next to your proton, it's more likely strong. Again, these are general rules of thumb. These rules of thumb do not work in all scenarios. It's best to understand the concept ideally, but these are for snap judgments. And then electron donating are not electronegative elements. So you want electronegative elements, and you don't want elements that are not electronegative. So the classic example of a not electronegative element is which element? Carbon. So the more carbons close to your proton, the weaker that acid will be. They're what's called electron donating. Okay? So the snap judgment things are here, 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 and here. Okay? Those things make something a stronger acid. If you're asked about a stronger base, it's the opposite, whatever this is not. So you just do the reverse for everything. Okay. What types of problems could you see? I think there's 3 types that come to mind at this moment. There could be more, but the ones I'm thinking of is just a comparison. So I give you a comparison of 2 plus acids or bases, and you tell me which one's the strongest. So this could be acids, which is, well, I guess I'm putting 2 categories in one type here. Acids or bases. So acids, you follow what I circled. Bases, it's the opposite. So now, I guess there's only one other type, is if you're looking at one molecule, but on that molecule you're trying to find the acidic proton. Okay? So on one molecule, which proton is going to be donated first? You don't really have, in Chem 2B, you're not going to find the reverse. You're not going to find a basic complement to this, usually. If you find one on one of my old tests, I just can't think of it right now, but you can show me it in our next section when we get to 9:30. Okay, so let's do some examples now. Let's say we have this versus, okay, and I'll number them, 1, 2, 3. Strongest acid is? I'm going to pick 3 because it's got the electronegative element closest to the proton that's going to be lost, which is this one. So this is the proton going to be lost. There. That chlorine, so I'm going to put this as the winner. Yes, you win. It's got the chlorine closest to it. What's the next one? 1 is in the middle, and the worst one is 2. It has no chlorine at all. It's just got carbons. Carbons are the worst. Okay, the other ones have carbons. By the way, is that proton that I underlined the only proton in any of the molecules? Or are there other hydrogens? There are others. Let me just draw the other ones in the middle one. Okay? The other ones, there's 2 here, there's 2 there, and there's 3 here. Why is that proton, the one I underlined, the strong one, and not those? Yeah. The one on the right, where my green pen is on an oxygen. The all 1, 2, 3, 4, 5, 6, 7, the other 7 on the left are on carbons. If you look at the periodic table, according to electronegativity, as you go across, you become stronger. So the ones on oxygen, to the right on the periodic table, are stronger than the ones on carbon. That would be, the question I just asked is, what is the most acidic proton? So that is a style of question, type 2 there. Find the acidic proton on one particular molecule. Okay? Let's try a different example. Right or left? Stronger acid. The one on the right here, I'll put a star by it. Why? It's going to have resonance. Yeah, here. When you lose that hydrogen, it'll have resonance within here. This has no double bonds. It's just sp3 carbons on the left-hand side. Okay, let's try that again. Okay, right or left? This one, because there's more oxygen, there's going to be more resonance. Same thing, the O2. Gosh, I'm running out of examples here. Does this make this one weaker or stronger? If I just did that, see that? I'll put it in a different color. Weaker. That makes it weaker if I put a carbon there. This, stronger. Kind of see how it works? So if I did this, I'll draw it if you missed it. If I put a carbon there, it's going to make it weaker. If I put an electronegative element there, it's going to make it stronger. Okay, so there's all kind of fun ways I can mess with this. Okay, a couple others of you had other, I think, resonance or alpha hydrogen questions. Save that to the end if you have a particular example. I'm happy to do that one. Okay? All right. Did I miss anything else with acid strength that you're psyched about? Okay, I want to do Ka versus Kb, pKa, pKb, Lewis acid, Bronsted. I want to do all those 3 right there. Okay, all together. Let's Let's do it. Okay, first of all, if you have an acid, you should be able to write any class the general equation for an acid. Your instructor might have called this something different if you're in a different class, but I'm talking about this. Or if it's a base, A minus, you should be able to generate this kind of reaction all by yourself. Okay, so then you should be able to write the K for each of these. Because the first one's an acid, I'm writing Ka. It's actually a Kc. We just write the A for fun because it's an acid. That's it. It's really a Kc. So you should be able to generate this equilibrium expression right here. I don't include water because it's a liquid, and then you should be able to include this expression as well. Or be able to write this expression as well if it was a base. Okay, so make sure you can write that kind of reaction. Again, water's not included. Make sure you can write in the state symbols. I didn't write in the state symbols here. All right, so your instructor will probably, I will definitely give you this, Ka times Kb. Okay, in order for this equation to work, the acid and the base must be blank. Conjugates. Yeah, you must have a conjugate acid and a conjugate base. Remember, Kw is a constant. It should also be given by all instructors on the exam. 1.0 times 10 to the minus 14. By the way, the reaction that you should be able to write the reaction that goes with this. Let me write it. Okay, is this reaction favored? Yes or no? No. How do you know that? Because Kw is small. When I say Kw is small, because I said it, I'm comparing it to what value? The number 1. So if it's smaller than 1, you expect the reactants to be favored. Okay, do we know which way this reaction shifts? With the information I gave you, there's no shift. I have to say something is added, and it will shift right or left, or something is subtracted, and it will shift right or left. So just seeing this has nothing to do with shift. If I want to talk about shift, I'm comparing what two values? K and Q. K and Q has to do with shift. Okay, so you're no longer comparing to 1. When you compare K to 1, you're talking about which side is favored. That is totally different than shift. You could have the right-hand side favored and it shifts towards the right-hand side. Or you could have left-hand side favors and it shifts away from that. It doesn't. So favored and shift are not necessarily connected. All right, so this can be written differently. You can take the pKa, and that's just the negative log of Ka. Okay, so pK anything is just the negative log of that thing. So this can be written differently. Some of your instructors, and I think I have already myself, can write it out like this. pKa plus pKb will end up being 14. So a lot of these equations will give you on the back of the exam, or some variation of them. Okay, if Ka is large, let's do some concepts here. Ka is large, pKa is large or small? Small. The negative log causes it to go the opposite direction. Okay. The stronger the acid, the more Ka is a large or a small number? Yeah, so if the acid is strong, Ka is large. If the acid is weak, if the acid is strong, Ka is large. If the acid is weak, Ka is a small value. If there is a shift in the system, how does Ka change? Say the concentration changes. It doesn't. It's a constant. It's called the equilibrium constant. It doesn't change. As far as you're concerned, it only changes with temperature change. Okay, let's write down a few things here. A lot of things. I'm just going crazy here. This is just, can't control myself. Okay. I'll give you a second. Circle all the things that are affected by concentration change. So what are all the things in this list that are affected by a concentration change? I'll give you a 10-second head start on me. All the things in this list affected by a concentration change. Okay. Those of you who want to work with me, I'll start from the beginning. Those of you who want to keep working, totally fine. Yes or no? No. Nope. Okay, pH changes. So that means a strong acid has a pH around what number? 0, maybe 1. Can it go larger than 1? Yes, if the pH goes where enough, if the concentration of H3O plus goes where? Down. So if you have an initial molarity that smaller and smaller it gets, you can have an acid that has a pH that goes up and up. So can a strong acid have a pH near 7? Yes. Yeah, if you have a really, really low concentration of the hydronium ion. So you can get a pH of 6.99 for a strong acid if you have a really low concentration. Affected by concentration? Yes. 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 Okay, see how that works? So know what's affected, what's not. The K's, they're constant, so they're not going to change. Okay, that was K's. Let's talk about acidity and basicity if there's questions about that. Okay, you want to know your definition. So the Bronsted-Lowry definition, sometimes you might see a problem as such. Let me see if I can think of a way to write it. Yeah. Let me write two reactions here. That one, and I want to write this one down here. I'm going to leave a little space in between them. Okay. All right. Acid or a base? Right there where my pen is. Yeah, you know it's an acid because it donates a proton. So this is base. I'll do the easy one. If that's acid, that has to be a base. This is conjugate base that goes with this one. These two go together. And this would be the conjugate acid. These two go together. Okay? So this could be a sort of problem, often multiple choice, but it could be written out like this as well. Identify all the acids and bases. And often when it's this style, it might say in front of it, Bronsted-Lowry acids and bases. This is just a common way it's worded. All we want to know is what's acids and bases. Okay, this is base. I'll do this acid. This is conjugate acid goes with that one, and the conjugate base goes with water. Okay, so make sure you can label those or do a multiple choice related to those. Lewis can be way more exciting. They're not this kind of standard. They don't always have conjugates, and sometimes they don't. Lewis is more generic. Let's say we have this. Oh yes, I really like this one. Okay, I'll give you a moment to figure out which one's the acid and which one's the base. You're going to have to use the Lewis definition to get it right. I need to get a different color to solve this one. 10 more seconds. And the acid and the base. What's this? Yeah, this is the acid. It's the base. There's no conjugate in this example. How do I solve this? K plus. Remember, I'm going to ignore the K's because they're spectator ions. Because they're neutral. I know they're neutral because they're conjugate of a strong base. So any conjugate of a strong acid or base is always neutral, or we call them in 2A a spectator ion. So these are lame. They do nothing for me. Okay, the base, this, if I put the lone pairs, this, or the thing with the more negative charge will be the base. That's one easy way to identify it. It's going to use its lone pair to donate to here to make that I3 minus. So one way to identify things, the more negative thing, if one's more positive and one's more negative, usually, not always, the more negative thing is the base. So this is a classic Lewis acid, Lewis base problem. Let me just do a weird one. I think this will work. No. Yes. Okay, I got it. No. Okay. Yes. Now I got it. No. Yes. Okay. Now I think I'm okay. Yeah, this is what I wanted.
Wait, no.
Took me a second. There we go. That's what I wanted. Okay. Acid or base? Yeah, so the base, the acid, the conjugate acid, and the conjugate base. Look at these pair here. Sometimes it's hard to tell, especially with a polyprotic, which one's the acid, which one's the base, because they both have a negative charge. Okay, so you see how they both have a negative charge? Usually the acid is more positive, like if you compare these two, this has the positive charge, this is neutral, so this has to be the acid, this is its conjugate. But when they're from a polyprotic, they can both be negative, but you'll see the acid is the one with more protons, or the slightly more positive charge, even though they're both negative. Okay. That's all the Lewis, so just make sure on my practice exams, I think your instructor should have practice exams, when they have Lewis ones, those are the ones that can be a little bit trickier for some people. This one's one of my favorite, most tricky that I've ever thought of once. Okay. All right, I want to do a little bit of acid, base, or neutral. Acid, base, or neutral. That's that category there. This, in your class, might have been called also the salts or ions kind of section. Let me write down a couple examples here. Okay, there we go. All right, I want to know if these are acidic or basic or neutral. That would affect how I do a pH problem. If I'm doing a pH problem, I need to know if it's an acid or a base, really. If it's neutral, I know the pH is 7, but if it's an acid or a base. So how I do these, if you're from a different class, you might do these a little bit differently. You can start doing these in your head once you kind of get used to the idea. But what I do is I think of the ions separately. I evaluate them. I think of their conjugate, or the conjugate, either one of those, if you think of it, is fine. And the conjugate of this one is HBr. So the way I think of it, if this is acid, base, or neutral, I look at the conjugates. This, anybody, is what? Acid or base? Acid, and specifically, strong acid. Let me get a different color. Strong acid. So the conjugate of a strong is neutral. So that part of the ion is neutral. This is acid or base? Base. So this is, the conjugate is just a regular acid. So this compound is made of an acid and a neutral. This is acidic, or an acid. Okay, so that's how I think of them. Let's try a couple of others here. The strontium, I forgot a 2 there. So this one is made of a strontium 2 plus and an I minus, really 2 I minuses. The strontium comes from strontium hydroxide, and the iodine is a conjugate of HI. Okay, HI is what? Specifically, it's an acid, but it's a strong acid. That means its conjugate is neutral. Strontium hydroxide is strong base, so that its conjugate, strontium 2 plus, is neutral, because any conjugate of a strong is neutral. A neutral plus a neutral, this is just neutral. People not in my class, okay, my class, quiet, let's just quiz the other class. How do you know if something is a strong or not? Meaning in the category of a strong acid or strong base. Okay. I'm not disagreeing with you. Let me give you another way of thinking about it. Yes? Yes, it dissociates on. True, true. But to identify it, because you're looking at something, you don't know if that thing dissociates 100%. You just memorize this table. Okay? If it's on here, it's strong. Now, why is it on here? That's the acid, relative acid-base strength, which you two were both talking about and other people were mumbling. But you've got to know these as a snap judgment immediately, because you know all the conjugates of all of these are neutral. And it helps you do other problems. If you don't know these, you're going to be at a deficiency compared to everybody else who does know them. Okay. Now, these have to be in the aqueous state, by the way. If they're not in the aqueous state, this doesn't work. So these are, it's all assumed aqueous. Okay. That was page 73 of my reader if you needed it. It's also in your textbook in like chapter 5 or something. I'm going to skip that one for a second. You can do that at home with your friends. Okay, let's do this one. How would I solve this last one? Yeah, you don't need to do this craziness here. This is just one of our strong bases I showed you literally 5 seconds ago. So if it's something you recognize, you don't have to go through this garbage. This is not a salt or ion. Okay? If I said water, you're not going to go through some crazy thinking here. You just know it's neutral. Okay? So if you give you something that you recognize, it just is. Okay. I want to talk about, any questions on that before I move on? I'm trying to get everything in here. We're making good progress though. I want to talk about finding pH. I'm going to flip to a page I showed you earlier. No, I want to flip to a different page. This is the end of my acid-base part 1 chapter, or in my reader, chapter 15, last page, 90 kind of. I want to show you this. This is page 90 of my reader. Page 90 of my reader. Okay. Here's on the bottom is an abbreviated table of the ice table. What I want to call your attention to is some of the things up at the top there. So you're going to use an ice table. This is kind of written at the top and the bottom. If you're asked for pH, okay, if you're asked for pH, you have to separate into 2 categories. Is the thing I'm asked for pH strong, or is it not strong? Okay, that's weak. If it's strong, again, how do you know if something's strong? It's on that table I showed you now a minute ago. Okay, so if it's strong, will you use an ice table? No, don't use an ice table in pretty much all circumstances. You're just going to use a set of formulas. Maybe it'd be easier if I show you the beginning of this chapter. Sorry, I'm flipping around a lot. I'm flipping out here. Being in chapter, I think a visual might be better. Yeah. This is page 66 of my reader. I'm showing you this right-hand side right here. If you have a strong acid or strong base, you're going to use a combination of those formulas right there. No ice table necessary. That's including if it's a polyprotic strong acid. What's one of your polyprotic strong acids? Sulfuric acid. It's your only one, in fact. Okay, you will use an ice table if you have a weak acid or weak base. No matter if it's straight up weak acid or weak base or comes from an ion or a salt. The previous examples we were doing were that acid-base neutral. Those were the salt ions. Okay, if it's any of the weak category, acid-base, polyprotic weak acid or base, or a salt, that's all ice table problems if you're asked for the pH. Okay, so make sure you're in that category. There's only one kind of weird one of all of these, and that's the dilute strong acid or dilute strong base problem. Other classes, do you remember that being covered? Okay, I will just say it verbally. If you remember that being covered, well, you should probably talk to your classmates if you're not sure. But if you have a dilute strong acid or dilute strong base, that means the concentration of the strong acid or strong base is near 10 to the minus 7. So if your concentration is near 10 to the minus 7, within a factor of about 100, you will use something that will look like an ice table. Different instructors teach it differently, so you can ask me later if you want to see me do one of those examples. But if it's one of those, that's one of those weird categories that's a strong acid or strong base, but you will use something that sort of looks like an ice table to solve it. No. Okay. Otherwise, make sure you know that distinction between weak acid, weak base, use the ice table, strong acid, strong base, do not use the ice table. Okay, polyprotics. Polyprotics. I want to say a little bit about that action. Let's use one that I wrote earlier today. Polyprotic has more than one proton. Let's write out its dissociation. And then it can lose 2 protons, so there's 2 reactions here. You should be able to generate these reactions all by yourself. So don't expect us to give it to you. We might if we're just feeling crazy, whatever. Okay, these Ks, this would be Ka1 and Ka2. There's a number of variants of these kinds of problems that could be asked. Make sure you can label the acids and bases and their conjugates for sure. If it is something like this, is this a strong or weak? Weak, it's not on the table, so that's how I know it's weak. Okay. Am I going to use the ice table if I'm asked for pH? Yes. Am I going to use the ice table if I'm asked for equilibrium concentrations? Yes. At one point, yes. Will I use the ice table more than once? No. No. Once only. All future dissociations or all future reactions, we're assuming all the protons come from here. So when you're doing a polyprotic, you're not going to use the ice table more than once, regardless of what question it is. You'll only use the ice table once if it's weak. If it's strong, you won't use the ice table at all. Which K is larger, Ka1 or Ka2? 1 is the larger, by a lot or a little? A crazy lot, yeah. So the first loss of the proton is always much, much larger. So is this first reaction, which side is favored, right or left? I like this. Question why. First reaction, which side is favored, right or left? I hear some people saying the products. That is not correct. It is the reactants in favor. Why is that? It's weak. It does not matter that Ka1 is large. It's large compared to Ka2, but not large compared to 1. How do I know that this is not large compared to 1? How do I know that this is not a large number in the general scheme of things? It's weak. Because this is weak, that's going to be smaller than 1, and so the reactants are favored. But this is even less favored, the second one. So Ka2 is much smaller, so the left-hand side is also favored, but even more than the top reaction. Does that kind of make sense? So in both cases, the left-hand side is favored, or the reactants are favored. Okay. Okay, anything I missed there that you have a question about before I do buffers and indicators? Okay. Let's talk about some buffers and indicators. We might not have time for indicators. We'll see. Buffers. Okay. I will tell you quickly about buffers. First of all, the buffers, do they need to be conjugates? Yes or no? Yes. Strong or weak? Weak. Does the acid and its conjugate both need to be weak? If the acid is weak, will its conjugate base be weak? Compared to strong acids and strong bases, yes, they're weak. If one's relatively weaker, the other one's relatively stronger, but they're not considered a strong acid or strong base. Do you get the distinction? I'll say it one more time. If you have two conjugates, if one's weaker, the other's relatively stronger, or vice versa. If one's stronger, the other's relatively weaker. But they are all weak compared to the strong acids and strong bases in the table that I was just talking about now like 5 minutes ago. Okay? So, they're both weak, both the acid and its conjugate. Are they of a similar molarity, yes or no? Yes, within a factor of 10, they should have a similar molarity. Should they be of a relatively large volume, yes or no? Yes, compared to anything that you add to it, yes. Okay? So those are the factors that are involved in a buffer. Let's say we have HA and A minus. If you're given a question, there's kind of two types of problems that involve just the buffer itself. The easiest would be given the concentrations, find the pH. That would be as simple as just plug and chug. I did a reversed example in my last class, which is a bit harder for most students if I give you the pH to go backwards and find these concentrations. Okay? I'm not going to do an example of that right now, but that is a type of problem where you're going this way to the pH or given the pH and go to the concentrations. Getting to the concentrations is a little harder for most folks. Okay, that's one pretty classic sort of question. Now, if you add something to a buffer, so let's say I'm going to add KOH to this buffer. Let's say this is 1.5 molar and this is 0.80 molar. Okay? And let's say we have 1 liter of solution, and I'm going to add a small amount here, 0.02 moles of this. First of all, which one will this KOH react with? HA or A minus, both or neither? HA, that's right. How did you know it'll react with HA? This is an acid, and that's a base. Acids and bases go together. A base won't react with another base in our class, and acids are not going to react with other acids. Okay, so I'm not going to write the K because it's a spectator ion. I don't include spectator ions in my class. You can, it's not a big deal. You should be able to generate this reaction, A minus plus H2O. So again, I've added KOH to my buffer. I'm trying to figure out what happened. Why did I write the arrow just going to the right? Because I have a strong base here. That means that anytime I have a strong acid or base in the reactants, it's going to push the reaction 100% to the right. Okay, I have a strong base in this case, it's going 100% to the right. Okay, let's see what we've got here. I'll do a different color. This was one. 0.5, this was 0.80, and this was 0.020. Because I'm 1 liter, these are the molarities are the same as the moles. Okay, let's say I wanted pH after I added the KOH. If I want the pH, can I use an ice table now? Yes or no? No. Can I use the Henderson-Hasselbalch now? No. What do I have to do right now? Well, in my class I called it a stoichiometry problem or a stoichiometry problem. I think that's what I called it. Okay. I have to do stoichiometry. How do I know that I have to do stoichiometry? There's a couple ways to answer this. Okay, the more complicated way, but the true concept is you look at the unfavored side, right or left? Right. Left, because there's 100% there. Left-hand side, I need a 0 here in order to start an ice table. You need a 0 on the unfavored side. There's another way you could have known it that works for buffers but not future problems you're going to see in your class, which is anytime I add something to a buffer. So I've got my buffer, anytime I add something to it, I have to do stoichiometry before going to ice or Henderson-Hasselbalch. One more time. Anytime I add something to a buffer, I must do stoichiometry. I'm about to do that right now. Before I use Henderson-Hasselbalch or an ice table. Okay. So what I'm going to have to do is find the limiting reactant. That's the smallest number. I'm going to subtract that off on the side it's reacting away from. 0.020. I'm going to add it to the side it's going to. So I'm following the 100% arrow. I ignore water because it's a liquid. I add these up. Oh gosh, 1.48 moles, 0.82 moles. Okay, that's stoichiometry. Okay, I figured out how it's going to react. Now what do I do to solve the problem for pH? Now, can I go to Henderson-Hasselbalch, yes or no? Yes. Could I go to ice table? Yes. Do I need to do more stoichiometry? No, I'm done. I just did it. I don't need to do it twice. So, now I can go to Henderson-Hasselbalch, or the true concept is, see how I have a 0 on the unfavored side. Okay? Alright, so you would go pH equals pKa plus the log of the base. What number goes up here? I know the base. I was looking for a number. 0.82. But thank you, who said that. You are so right. I want to affirm your thoughts in life. Well, maybe not life. I don't know what you're doing. Okay. So, then where would I find the pKa? It's a negative log Ka. Okay, where do I find the Ka? If you're in the test, it's either in the question or on the back of the exam. One of those two places. You have to be given that Ka. Alright. Is this going to change the pH a lot or a little? A little. Is the pH going to go up or down? Up. How did you know? I added a base. It better go up. And I knew it was a little. How did you know it was going to go up a little? Because it's a buffer. The buffers don't change pH very much. Okay. I'm going to pause right there. How is that for everybody?
Great.
Good? Good. Other people, how are you feeling? Other classes? Good luck on your second exam. If you have questions, I'll answer your question first. I assume it's on this. I'll leave this up. But let people leave because they want to go watch the Oscars and stuff.